Great. So let's quickly recap. Last time we talked about possibly the two most important concepts in this class, and the two concepts from which basically everything else in this class is going to be derived. What were the two major concepts that we talked about in the previous lecture? The two conservation laws. Yes. Exactly right. So we talked about the conservation of mass and the conservation of momentum, and I went through a derivation of the conservation of mass for a control volume of fluid. So conservation of mass basically states in plain English that the rate of change of mass within a fluid control volume is equal to the mass flow rate in minus the mass flow rate out. So we took a look at this concept mathematically for a conduit that may be flowing partially full, that may fill or empty over time. And we derived the following expression by dividing by both the density of the fluid and the length of the control volume. That we have that the conservation of mass is equivalent to the rate of change of area plus the flow rate out minus the flow rate in over the length of the control volume is equal to 0. If we took the limit of that expression as delta t goes to 0 and delta x goes to 0, we end up with the following expression. This is the general differential form for the conservation of mass that you might see implemented in a fluid solver. Let's just quickly review what each of these terms means. The dA by dt, this refers to the rate of change of mass, or equivalently volume, within our control volume. And the second term refers to the mass flux through our control volume. So in other words, this would be the flow out minus the flow in. So just a note that when we're expressing something in terms of a derivative of the flow over some differential distance, the convention is out minus in rather than in minus out, because we're looking at the difference over the interval with the right edge corresponding to out, the left edge corresponding to in. All right, any questions on conservation of mass in the general case? Yes.
Could you reiterate the terms mass and volume? Like, why are those interchangeable?
They're interchangeable because the density is constant.
Oh, yes.
So we can just divide each term by the density without changing anything. Any more questions on general conservation of mass? All right. So next, we looked at the specific case of pressurized pipe flow, which is going to encompass the first part of the course. And we found that we could simplify the conservation of mass for pressurized pipe flow. So for the change in mass within the control volume, or the change in volume, what did we say that term could be simplified to? 0, right? Because the pipe is flowing completely full, and thus the volume within our pipe isn't going to change, and thus the mass within our pipe isn't going to change over time. So the change in mass over time within the pipe is going to be equal to 0, assuming the pipe is flowing completely full. We also said that the mass flux through the pipe has to also be equal to 0, right? If the volume in the pipe is not changing, then the flow into the pipe has to equal the flow out. All right, any questions on this concept? Yes.
And the A in the top part, is that referring to the cross-sectional area?
Cross-sectional area, yes. So remember that from our original expression, when we were performing our mass balance, we divided by the length of the control volume and also the density. So that's how we ended up with dA by dt as representing the change in mass or the change in volume. Okay, good questions. Any other questions on conservation of mass or pressurized pipe flow? All right. Now, in the second half of yesterday's lecture, we started to talk about the conservation of momentum, conservation of linear momentum for a fluid volume. And conservation of momentum is basically Newton's second law, right? Which from Physics 101, you applied in the form of F equals ma. So the sum of unbalanced forces acting on a body is equal to the mass times the acceleration. But we were able to generalize this for the case of fluid flow by stating Newton's second law in a more general way, particularly the sum of forces acting on our fluid body is equal to, what does this term on the right represent? That is correct. So this is the time rate of change of momentum, which for the case of a solid body is just equal to the mass times the acceleration. But we generalize this for the case of fluid flow. So I want to recap a little bit on conservation of momentum because I felt a little rushed last time I was going through it, and I would just want to make sure everything is clear. So we applied conservation of momentum by first applying a force balance to a pipe section, and then also looking at the rate of change of momentum within that same pipe section. So quickly, let's recap. So what are the major forces acting on a fluid in a pipe? I have some hints up here, but what were the three major forces?
Gravity.
Gravity. So there's a force imposed by gravity. If our pipe is not completely horizontal, there'll be a component of that force in the direction of flow. And so the force due to gravity will be equal to the mass times the acceleration due to gravity times sine theta, where theta is the angle from the horizontal. Okay, what's another force acting on our control volume? Yes? Friction, very good. So if the water is flowing in the pipe, there will be some resistance to that flow imposed by friction on the pipe walls. Okay, very good. And the final force? Yes. Pressure. So we have our net pressure force. So that's going to be the force exerted by pressure on the upstream end minus the force exerted by pressure on the downstream end. So we took all these three forces, we added them together, and then we equated them to the net rate of change of momentum. And we got the following expression. So let me just break down each of these terms here. So this first term, this is the rate of change of momentum within our control volume. So due to changes in the intrinsic properties within the control volume. The second term is the net momentum flux through the control volume. And I know there was a question on this last time, so I'm going to come back to it briefly. This term here, this is the net pressure force. This term here, this is the gravitational force. And this term here is the frictional force. So tau is the mean shear stress. P is the wetted perimeter. This is a capital P. Our pressure is in undercase. So the mean shear stress times the wetted perimeter times the length gives the total frictional force. And let me just make a note here. This mass, this can be re-expressed as the density times the volume, which is equal to the density times the cross-sectional area times the length. So there was a question last time about what momentum flux means, and I thought about how to convey it. So I would say to start by thinking about mass flux through a control volume. So let's say, I'm just going to draw this down here. Okay, let's say we have some control volume and we have some particles of mass. I'll draw them in blue here. And these particles are traveling to the right. So you can conceive of the mass flux as basically taking the number of particles that are coming out of the right side minus the number of particles that are coming in on the left side, right? So you just count up those number of particles coming out minus the number of particles coming in, and that's kind of conceptually how you can think of the mass flux. The momentum flux is similar, it's just kind of a more generalized case. So you can envision each of these particles having some velocity. So each of these particles has some velocity. Maybe they're different. Maybe this has little velocity. Maybe this one has a lot of velocity, and so on. And it's kind of the same idea. You just take the product of the mass and the velocity for each of those particles going through the right side minus the product of the mass and the velocity coming in through the left side. So it's just a generalization of thinking about mass flux. Okay, are there any questions on that concept? Yes.
Can you say that again? Was it the product of velocity and mass?
Yes, so momentum is the product of velocity and mass. So we're taking the product of velocity and mass for each of these particles, summing it up as it comes out the right side, minus the sum of the mass and velocities coming in the left side. So it's just it's a generalization of thinking about like a mass flux. All right, so going back to this equation, we can simplify our momentum balance by dividing by both the density and the length of the control volume. So I'm going to do that. I'm going to move on to the next page here. If we do that, we get the following expression. So the flow at time t plus delta t minus the flow at time t divided by our time increment delta t plus q out u out minus q in u in divided by delta x is equal to g times quantity p in a in minus p out a out divided by the acceleration due to gravity times rho times delta x. So what is the acceleration due to gravity times the density? It's another term. I heard someone whisper it. Heard someone say the correct answer. Specific weight. Very good. So we can replace that g rho by the specific weight. Okay, and then we're going to have plus quantity g times the cross-sectional area times sine theta plus negative tau times the weighted perimeter divided by the density. And we're pretty much there, but I made two simplifications. This is just the way that it's expressed, and we're going to need it today when we talk about the energy equation. So let me just make these two simplifications clear. The first is we're going to take this sine theta term and we're going to approximate it with the bottom slope. So if we have a small angle of inclination, which is almost always going to be the case for pipe flow in a large pipe system, we have that the bottom slope, which is equal to negative delta z divided by delta x, so this would be the rise over the run, is approximately equal to sine theta. So note that here I'm referring to kind of a triangle like this. This is our angle theta. This is delta x. This is delta z. In this direction, it would be negative 12. Okay, so the sine theta term is approximately equal to the bottom slope. And then we're going to define a term called the friction slope. You may have heard this term in fluid mechanics, but we're going to define it as the mean shear stress tau times the wetted parameter divided by the acceleration due to gravity times the density times the cross-sectional area. So this is called the friction slope. What it really is it is the energy loss per unit length due to friction. We're just going to define this term for convenience. And again, this is going to be used later when we start talking about the energy equation later today. So if we take these two terms and substitute it back into the previous equation, we get the following. So we have the flow rate at time t plus delta t minus the flow rate at time t divided by delta t plus our net momentum flux. So that's Q out, U out minus Q in, U in divided by delta x, the length of our control volume, is equal to the acceleration due to gravity times P in, the pressure at the upstream end, times A in, the cross-sectional area of the upstream end, minus P out, A out, the same two quantities for the downstream end, divided by the specific weight times delta x, plus G times A times the bottom slope, minus G times A times the friction slope. And again, just like with the conservation of mass, we're going to take the limit as delta x, the length of the control volume, goes to 0, and delta t, our time increment, goes to 0. And we get the following general equation for the conservation of momentum. Let me give myself a little more space here. dq by dt, so that's the rate of change of the flow, plus dqu by dx, so this represents the net momentum flux, plus g times a, that's gravity times the cross-sectional area, times the following quantity, 1 over the specific weight, times dp dx, so this is the pressure gradient, minus the bottom slope plus the friction slope is equal to 0. Okay, so this looks really scary, but it's fundamentally just Newton's second law applied to a control volume of fluid. Let me go ahead and just write out what each of these terms means again. So this is the rate of change, or represents the rate of change of momentum within our control volume. This term here represents the momentum flux through our control volume. This term here represents the pressure force. This term here represents the gravitational force. Gravitational. And this term here represents the friction force. So again, it looks really scary, but fundamentally what it is it's an application of Newton's second law to a fluid control volume. Yes.
Views about the signs for the friction force. So did it change to positive from negative somewhere? Up there it's minus PAS.
Right. So the bottom slope and friction slope will generally have different signs, but I believe it's because this quantity here had a negative sign in it. So I'm going to post the full derivation in terms of my type notes shortly. So after we complete this module on conservation laws, I'll go ahead and post that just to make sure that I didn't make any mistakes in my derivation here, but I'm pretty sure that what I have is correct. If you find an error, they'll let me know. Okay. All right. So believe it or not, we're going to be using this equation throughout the class. We're going to use it today to derive where the energy equation comes from. It's fundamentally just a force balance applied to a fluid volume. We can simplify this equation a little bit more for the case of pressurized pipes, and that's what I'm going to do next. So let's test your calculus skills here. This simplification is going to help us out later. So first, let's take a look at these terms. Let's take a look at the momentum flux term first. So we have dQu by dx. Does anyone remember the product rule from calculus? What would this become if we apply the product rule? Yes. Yes, that is correct. So we can write that as Q times du dx plus U times dQ dx. All right, so if we think back to the conservation of mass for pressurized pipe flow, what is dQ dx? 0. So this is basically the volumetric flux through our control volume. So the flow out minus the flow in. For a pressurized pipe, this term has to be equal to 0 because the flow out is equal to the flow in. Okay, next, let's look at this other term here, dQ by dt. How can we re-express Q, the discharge, in terms of other variables we might know? Yes, so the discharge Q is equal to the velocity times the cross-sectional area. So this is d of quantity AU by dt. We can apply the product rule just like in the first case. So we'll have U times dA by dt plus A times du by dt. So from the conservation of mass, which of these two terms is also equal to 0? The first one or the second one? The first one, right? The dA by dt term is equal to 0 because the volume in the pipe is not changing over time, and thus the cross-sectional area of flow within the pipe is not changing over time. So this first term becomes 0. And we can simplify our conservation momentum equation for pressurized pipe flow. So let's go ahead and do that. If we take our previous equation and substitute these simplified terms in, we'll get A, the cross-sectional area, times du by dt, plus Q, the discharge, times du by dx, plus G times A times 1 over gamma times dP by dx minus the bottom slope plus the friction slope is equal to 0. And let's go ahead and just divide by the cross-sectional area. If we do that, we get du by dt plus, what does this term become here? We divide by the cross-sectional area. Right, so this becomes u. So we'll use u in this class instead of v because v we'll be using for other things. So this becomes the velocity times du by dx. And then this term just becomes g times the quantity inside here remains the same. So 1 over the specific weight times dp dx minus the bottom slope plus the friction slope is equal to 0. So this is our conservation of momentum and conservation of mass together, because we used conservation of mass to simplify these different terms. So this is conservation of mass plus momentum for a pressurized pipe. All right. And that concludes our derivation. So are there any questions on how we arrived at conservation of mass or conservation of momentum before I move on? Yes.
For the Q, you just made it into the AU, right? And it's about the A's.
So I divided the first equation by A. So the first term, A goes away, Q becomes U, and GA becomes G. Good question. Any questions on this derivation? Okay, let's go ahead and apply conservation of momentum to an example problem. Let's say we have a pipe. It's a horizontal pipe. It has a constant diameter of 6 inches. So our diameter is going to be 6 inches. The flow rate through the pipe is Q is equal to 20 cubic feet per second. And again, the diameter is constant, so I'll say the diameter here is also 6 inches. The pipe is going to be 20 feet long. So delta X is equal to 20 feet. And it's under steady state conditions. So the flow rate is not changing. And let's say we take 2 pressure gauges and measure at an upstream point and a downstream point. And the pressure at the upstream point is equal to 60 pounds per square inch. And our pressure at the downstream point is going to be equal to 55 pounds per square inch. And I want to know 2 things. First, I want to find the force exerted by friction over the entire length of the pipe. And second, I want to find the energy loss due to friction. Okay, so for the first problem, what's our general approach going to be? What do you think our general approach is going to be to find the force exerted by friction? What equation would probably help us? What equation involves forces? Conservation of momentum, right? So we can treat this kind of like a statics problem and apply a force balance to the fluid in our pipe. You probably did something similar in fluid mechanics. So we have that the sum of forces acting on the fluid in the pipe is equal to the time rate of change of momentum. So this will be equal to, let's see, it'll be rho times dq by dt plus rho times q out, u out minus q in, u in. Okay, so what about this first term here? The system's at steady state, so what happens to this first term? It's equal to 0, right? The momentum is not changing in our control volume over time. Okay, what about this second term, the momentum flux? Is it going to be 0 or no? It's not going to be 0. Let's think about the different terms in this equation. Okay, so Q out and Q in, are they the same or different? Q in is equal to Q out. What about U in and U out? Are they the same or different? They're different? Okay, so why are they different? There's a difference in the pressure. Let's think about it in terms of this pipe here. So we have Q is equal to 20 cubic feet per second. What is the area at the upstream end? It's going to be, yeah, so it's going to be pi over 4 times d squared. Okay, so this is pi over 4 times 6 inches squared. What's the area at the downstream end? Same. So are the velocity at the upstream and downstream end the same or different? They're the same. They have to be the same because the flow rate is the same at both ends and the area is the same at both ends. So it doesn't matter that the pressure decreased. The velocity is still the same. So that means that this second term is equal to 0. So the second term is equal to 0 as well. So we have, luckily, that the sum of forces is equal to 0. Okay, so we have that the sum of forces is equal to 0. What are the forces that we have to consider for this system? Okay, so we'll have pressure plus friction. What about gravity? Why does gravity not matter in this case? Right, so it's a horizontal pipe, so the component of the gravitational force in the direction of flow will be equal to 0. All right, so let's go ahead and write expressions for the pressure force and for the frictional force. I'm going to go ahead and advance to the next slide just so I have enough room. Okay, so the pressure force plus the frictional force is equal to 0. The pressure force will be equal to P1A1 minus P2A2. And the frictional force is unknown, but we know that it's going to be acting opposite to the direction of flow, so it's going to actually oppose the net pressure force. So I'm going to go ahead and write this as FP minus FF instead of FP plus FF. And same back here as well. Okay, so the frictional force is unknown. We can rearrange for the frictional force. FF is equal to P1, A1 minus P2, A2. And from before we have that A1 is equal to A2 is equal to A. So we can write that the frictional force is equal to A, the cross-sectional area, times P1 minus P2. That's going to be equal to pi times d squared divided by 4 times quantity P1 minus P2. This is going to be equal to pi times 6 inches squared divided by 4 times quantity 60 pounds per square inch minus 55 pounds per square inch is equal to 141 pounds. Okay, so there'll be a similar problem on your homework. For that problem, you'll also need to account for the gravitational force, but the overall setup of the problem will be roughly the same. Okay, so that's how we can compute the total frictional force in pounds. How can we find the energy loss due to friction from this frictional force that we computed? So we have the force exerted by the friction of the pipe. How can we compute the energy loss that's associated with that frictional force over the length of the pipe? Think back to physics. Sorry? So we have a force that's acting over some distance. How can we compute the energy loss associated with that force over that distance? Did I hear work? Someone say work? So we can find the work exerted by that force by integrating our force over the length of the pipe. So work and energy are equivalent. We have from physics that the work exerted by the frictional force is equal to the integral of our frictional force with respect to the length of the pipe. Okay, so we're going to take the integral of ff dx over the length x of the pipe. So our energy loss due to friction, this is going to be the integral, the definite integral from 0 to delta x of ff dx. This here is the energy loss due to friction. And because the frictional force is just a constant, this is just going to be equal to ff, our frictional force, times delta x, the length of the pipe. So we'll get 141 pounds times, what was the length of the pipe? 20 feet. And what we end up with is a frictional energy loss of 2,820 foot-pounds. Okay, so we could determine the energy loss associated with the frictional force by integrating that force over some length of our control volume. How does that imply that the energy equation and the momentum equation are related? How do you think we're going to arrive at the energy equation from the momentum equation that we derived? If work is the integral of a force over some distance, how do you think we're going to arrive at the energy equation from the momentum equation?
You integrate the momentum.
Yeah, that's exactly right. So we're going to integrate the momentum equation over the length of our control volume. So let's go ahead and do that. Part of the reason I do these derivations is I want to make sure you know where different ideas are coming from. So we're going to go over how we arrive at the energy equation from first principles. It ultimately comes from the momentum equation. So it ultimately comes from a force balance. So we can derive the energy equation under the following assumptions or conditions. So we're going to assume the following. The first one is an important assumption to remember because the energy equation is not always applicable. So first, we assume that the system is at steady state. So the energy equation is a steady state formulation. It can't be applied to systems that are evolving in time. So the system has to be at steady state. In other words, all the time derivatives are equal to 0. Again, this is a very important consideration to keep in mind. You can't apply the energy equation to any system that is changing in time. The second condition is we are going to look at a discrete control volume and we're going to integrate the force balance between an upstream point and a downstream point. All right, so let's go ahead and derive the energy equation. Again, I want to derive it from first principles just so you know where it comes from and also under what conditions it's applicable. We're going to be using the energy equation a lot in this class. So starting from the momentum equation for pressurized pipe flow, we have du by dt plus u du by dx plus g times quantity 1 over the specific weight times dp dx minus the bottom slope plus the friction slope is equal to 0. All right, so which of these terms can we remove from the assumptions that we stated on the previous slide? The first one. So the system's at steady state, so du by dt is going to be equal to 0. So the next, I'm just going to divide everything by g. So I'm going to divide everything by g. We'll get u over g du dx plus 1 over gamma times dp dx minus the bottom slope plus the friction slope is equal to 0. Now, let's think about what the bottom slope and the friction slope mean. So can we express the bottom slope in terms of something over dx? Easy, right? So the bottom slope, this is actually equal to, well, by our conventions, this will actually be negative delta z over delta x. So it's going to equal negative dz by dx. Okay, and the friction slope, remember that I stated before that this is the energy loss per unit length. So this is going to be equal to, I'll just call this the energy loss per unit length. So this will be dE by dx. So you can just think of E as being the energy associated with that frictional loss. So we can go ahead and rewrite this entire expression. We get U over G times du dx plus 1 over the specific weight times dP dx. Sorry, that is a d plus dz dx plus dE dx, where dE dx is the basically the rate of energy loss due to friction. This is equal to 0. Okay, so you'll notice that all of these terms are derivatives with respect to dx. So we can now integrate this entire equation with respect to dx. So let's go ahead and do that. So let's apply an integral from some downstream point, some upstream point x1 to some downstream point x2. We'll have u over g times du dx plus 1 over gamma dP dx plus dz dx plus dE dx dx is equal to 0. So let's go ahead and separate out these terms. So we'll have 1 over g times the integral from x1 to x2 of u du dx. You know what? I'm going to stop writing these as partial derivatives because we only have one variable that we're using as our integrand. So u du dx times dx plus 1 over gamma times the integral from x1 to x2 of dP dx dx plus the integral from x1 to x2 of dz dx dx plus the integral from x1 to x2 of dE dx dx equal to 0. So you'll notice that for each of these expressions here, we have this dx in the denominator of our derivative and a dx here that we're integrating over. So we can essentially think of these terms as canceling out. So the dx's, our increments of integration, cancel. And we end up with the following. 1 over g times the integral of u du plus 1 over the specific weight times the integral of dP plus the integral of dz plus the integral of dE is equal to 0. And we can essentially just switch the limits of integration for each of these. So instead of integrating from x1 to x2, we integrate from u1 to u2, p1 to p2, and so on and so on. So this, we take the integral from u1 to u2, p1 to p2, z1 to z2, and e1 to e2. All right. So let's take a look at this first integral here. What would the indefinite integral of u du be? U squared over 2, very good. So if we just have some generic integral of some quantity x dx, this will equal x squared over 2, right? So we have that the integral of u du is equal to u squared over 2. So let's go ahead and write out these indefinite integrals for each term. So if we integrate u du, this becomes 1 over g times u squared over 2, evaluated from u2, or sorry, from u1 to u2. Okay, the next term we have is 1 over gamma times the integral of dp. So what is the integral of dp? P. So this becomes 1 over gamma times p, evaluated from p1 to p2. Next, in a similar fashion, we have dz. So the integral of dz will be z, evaluated from z1 to z2. And then this integral here, basically what we're doing is we're integrating the energy loss. So this term here, the integral of dE from E1 to E2, this becomes the head loss. So we'll just call this the head loss. And this is going to be equal to 0. So if we evaluate the definite integral, we'll get the following. This becomes u2 squared over 2g minus u1 squared over 2g plus p2 over gamma minus p1 over gamma plus z2 minus z1 plus the head loss is equal to 0. This probably looks familiar at this point. We can rearrange it. So I'm going to just put all the 1 terms on one side and all the 2 terms on the other side. And what we'll end up with the following: u1 squared over 2g plus p1 over gamma plus z1 is equal to u2 squared over 2g plus p2 over gamma plus z2 plus the head loss. And this is the energy equation. So you probably remember this from fluid mechanics. This is probably the equation that we're going to be using most extensively in this class. So we're going to be using it throughout the entire course. I would definitely commit it to memory. And just as a quick conceptual check, so each of these terms here are associated with a sum term in the momentum equation. This pressure energy term, or this pressure head term, this is associated with the pressure force. What term in our force balance is this term here associated with, the Z2 minus Z1? Which force? Gravitational, right? So this is associated with the gravitational force. This head loss here is associated with the frictional force. And what is this term associated with in our momentum balance? So this is the pressure force. What is this one associated with? You think back to how we derived this. Which term in the momentum balance? Yeah, the momentum flux. Okay, so that kinetic energy head, or that velocity head term, is associated with the momentum flux. So let me just put a couple labels on these. We still have some time left. So this here, this is the velocity head. As I mentioned, that's associated with the net momentum flux. This term here This is the pressure head. It's associated with the pressure force, and the Z1 here is the elevation head. That's associated with the gravitational force. This HL term, this is the head loss due to friction. That is associated with the frictional force. All right, any questions on how we arrived at the energy equation? Yes.
I'm sorry, it's not about the energy equation, it's about the example.
Is it something the class would benefit from, or? Okay, you can go ahead and ask it.
But yeah, I was just confused as to how the pressure changed. Was that because of the friction?
Yeah, so that would be caused by the friction. So that's just part of the information given in the problem. But that pressure change would be induced by friction in practice, yeah. And note that in the real world, that system would also depend on other boundary conditions in whatever system it's in. So for instance, what, pump is supplying pressure upstream, what's happening downstream, is there like a demand or something? So it's just part of the information given by that particular problem. Okay, good question. Yes.
There always have to be a pressure change though. Isn't that what's driving the
Yes.
forward? So even if friction wasn't there, there'd still be change in pressure, right?
Yes. So again, like all of these terms are connected. I would say to just, if you're trying to think about it conceptually, applying the tools that we give you in this class, like the energy equation and the force balance, will kind of help to answer some of these questions. But again, it's dependent on what information is given in the problem and other conditions in the system if you're looking at it in a real world problem. Note that it is possible for flow to occur even if there's no pressure difference, because there's other forces that could drive the flow. Right, so there could also be an inertial force, there could be gravitational force, etc. So you don't necessarily need to have pressure difference to drive the flow. It's just in practice for pressurized systems, that will be what drives the flow. So good question. Any other questions conceptually? All right, so what I want to do next is I want to go through an example applying the energy equation. So we're going to be using the energy equation a lot in this class. I want to start just by looking at a problem involving flow from a tank. It's kind of characteristic of the problems that we'll be looking at in this course. So let's say we have a tank. Okay, and oops, it's the bottom of the tank. Tank has some water level in it. And the tank is going to be discharging through a pipe. And the pipe is going to go underground. So this is the ground. So the pipe is going to go underground and it's going to empty into an underground reservoir. And for the sake of this problem, let's just say that this underground reservoir is vented. So it's vented to the atmosphere so that the air pressure in that underground reservoir is equal to the atmospheric pressure. So there's going to be water coming down through this pipe. It empties into our underground reservoir. There'll be some water level down there. And let's just put some legs on this tank here so it doesn't fall over. Okay, we'll say that the ground surface is at an elevation of z is equal to 0 feet. The exit of this pipe is 5 feet underground. So this is 5 feet underground from the center line of the pipe. I'll just draw that here. The pipe is 12 inches in diameter. The flow rate coming out of the pipe. So there is a flow rate out of the pipe, and it is going to be Q is equal to 3,200 gallons per minute. And let's say we happen to know that there's a head loss through this pipe of 11.53 feet. And our job is to find the height of the water in the reservoir H that will support this flow rate. So our job is to determine H, the height of the water in the reservoir. So let's go ahead and apply the energy equation. I'm going to apply it between 2 points. The first point will be at the very surface of the reservoir. And the second point will be right at the outlet of the pipe. So just as the pipe discharges into the air. So let's apply the energy equation between those 2 points. We'll end up with U1 squared over 2G plus P1 over gamma plus Z1 is equal to U2 squared over 2G plus P2 over gamma plus Z2 plus the head loss. Okay, so that seems like a lot of terms, but we can simplify our energy equation quite a bit. So our first point is at the surface of the reservoir. What can we say about the velocity head at the surface of the reservoir? It's probably close to 0, right? The water is not moving at the surface of the reservoir, so we can assume that the velocity head is approximately equal to 0. Okay, what about the pressure at the surface of the reservoir? It's equal to atmospheric pressure, so we'll be using gauge pressure in this class, so we can treat that pressure as basically being 0. Let's set our datum, our elevation datum at the ground surface. So what will Z1 become? H, right? So Z1 will be H. We're using our datum at the ground elevation. Okay, so at the exit of the pipe, what about the velocity head? Is it safe to assume that that velocity head is equal to 0? No, right? Because the water is moving at that point. We can't assume that the velocity head is 0. What about the pressure at the exit of the pipe? It's also atmospheric. So this term here will be equal to 0. What about our elevation head Z2 in terms of our datum that we've created? -5, very good. So this will be -5 feet. And then the head loss we know is 11.53 feet. So let's go ahead and re-express our energy equation. So we have H over here on the left side. On the right side, we have U2 squared over 2G, -5 feet and 11.53 feet. Let's just write it down symbolically first. So I have H is equal to U2 squared divided by 2G plus Z2 plus the head loss. we need to determine what this U2 term is. How can we do that? Cross-sectional area, so we apply continuity. So U2 will be equal to the discharge Q divided by the cross-sectional area. So that's Q over, I'm just going to use pi r squared in this case. So that will be equal to 3,200 gallons per minute divided by pi times, what would the radius be? 6 inches. So this will be 6 inches squared. And then we need to convert these units here, gallons per minute to cubic feet per second. So I will just tell you that for every 1 cubic feet per second, there are 448.83 gallons per minute. You don't have to know that number, but you can look it up. So if we go ahead and compute U2, we should get an answer of about 9.08 feet per second. So we can take that value for U2 and plug it back into our energy balance. We get that H, the height in the tank, has to be equal to 9.08 feet per second squared divided by 2 times 32.2 feet per second squared. Remember to use the appropriate value for the acceleration due to gravity in your unit system. So for US units, that's 32.2 feet per second squared. Z2, again, will be -5 feet, and the head loss will be 11.53 feet. So if we go ahead and compute this value for H, we get 7.81 feet. So that is the height in the tank needed to support a flow rate of 3,200 gallons per minute. All right, any questions on that example? Okay, so there's one more point I want to make before the end of class, which is about 5 minutes from now. So what units is the energy equation expressed in? Length, right? So it'd be expressed in units of meters or feet. Why is it expressed in meters or feet versus units of energy? So this is, I'm just going to ask this question rhetorically. Why is the energy equation expressed in units of length, so meters or feet, instead of units of energy, so Newton meters or kilogram meters squared per second squared? Yes. Yeah. So the answer is basically, it comes from how we derived the energy equation. So recall that when we derived the energy equation, we divided by 4 different quantities. So first, in the momentum equation, we divided by the density. And we also divided by the length of the control volume. And then when we converted to the energy equation, we also divided by both the cross-sectional area of our control volume, so that's A, and the acceleration due to gravity, G. So that gave us our answer in terms of head or hydraulic head. So that would be in units of length instead of units of energy. So let's think about what we divided by. So we divided by G times rho, the density, times the cross-sectional area, times the length of the control volume. So what is the product of these two terms here? The cross-sectional area times the length of our control volume is the volume of our control volume. Okay, what is the volume times the density?
Specifically.
So it will be, I think I heard it, the mass. Density times the volume is the mass. And what do we get when we multiply the mass by the acceleration due to gravity? The force of gravity, which is also called the weight. So what is head? What is hydraulic head and how does it compare to energy? The hydraulic head you can think of as the energy per unit weight. Okay, so if you're looking at the difference in hydraulic head between 2 points, that is the difference in energy per unit weight through the control volume. So just remember that head is not the same as energy. It's related, but it's the energy per unit weight. All right, so that's all I have for today. I will see you all on Tuesday.